We use powerful tools. Sometimes they're even fun, until we hit a wall, a bug we can't solve, a system that won't behave, or a moment where we start wondering if it's a skill issue. Then we enter the typical troubleshooting loop. We read the documentation, watch tutorials, or we call an expert paid by the hour to fix the problem remotely. Unreal Engine is a perfect example of this. It's incredibly powerful and it's used every day in production, from games to film to real-time visualization. But it's also massive, complex, and constantly evolving, making education and training feel like an endless path through steep terrain. And while there are many different guides and even a great community support, the learning content is external, meaning it lives actually outside your tool. Too often it's outdated, out of context, or simply not aligned with the exact problem you're trying to solve in the moment. So the question becomes, what if the engine itself looked at you struggling and decided to teach you how it actually works? My name is Enes Ayalp and I explored exactly that idea through PRISM, my CS master project at Georgia Tech. PRISM is an interactive learning framework built with Unreal Engine, delivered as a standalone project that turns the engine itself into a guided, hands-on learning environment. Instead of stepping outside to watch tutorials, you stay inside the editor and learn by actually working with it. You are not passively consuming content, you are interacting directly with the core systems like blueprint scripting, shader development with materials, and procedural content generation, guided step by step with real-time feedback. Before I showcase the tool's features, I want to emphasize the reasoning behind its design. I didn't arrive at these principles by chance. I derived them through a series of rigorous prototypes and tests where I intentionally hit walls to see where the educational friction lied. Starting from the idea to provide educational content from within the tool, I began exploring how this kind of support should actually look like. I began testing the Epic Games Content Examples project as an initial exploration. It demos features of Unreal Engine well out of the box, but it does not teach how to set things up really. Here, you're just adjusting values and observing results, not actually building anything. Then I thought, how about turning this into an educational game to actively challenge the learner? That introduced another problem. Important workflows like blueprint scripting are tightly integrated into the editor. Recreating that inside a standalone game would mean rebuilding systems that already exist, just most likely in a worse way. I wanted to keep the editor as it is and bring guidance directly into it. While testing out different approaches, I stumbled upon an interactive tutorial in another tool. It was unpolished and buggy, but immersion was there. It was a glimpse of what was possible, though it barely scratched the surface. I saw an opportunity to take that spark and transform it into a new standard for EdTech. My goal became clear. Build a scalable interactive system within Unreal Engine that pushes the boundaries of 3D learning. I have since dove deep into the engine's architecture to find ways to connect the just discovered dots. Meanwhile, I have had defined the principles, made design decisions, and these constraints took shape, all got formed into a framework called PRISM. At its core, PRISM is driven by 5 principles. Progressive, learning is broken down into step-by-step validation, where each part builds on the previous one. Real-time, feedback and validation happen instantly as the user interacts with the system. Interactive, the system responds directly to the user's actions, creating a dynamic learning experience. Support, when users get stuck, the system provides targeted hints and guidance to help them move forward. Mentoring, audio and visual cues deliver on-demand guidance, simulating the presence of a real mentor. These are the three components of Project PRISM. One key component of PRISM are interactive guides that run directly inside the editor. You hear and see the instructions through rich content like images and videos. And as you work, the system watches what you do, gives feedback in real time. This moves you forward automatically while saving your progress every step of the way. Then there is the comparison system. You hit play and your result is instantly checked against the reference scene. Not just right or wrong, you see exactly what's different, visually and in real time. You can even inspect those differences outside the engine. And finally, the experience becomes a game. You are dropped into the role of a robot inside a lab full of defects and glitches, and your job is to fix it so it can actually sustain. Now let's take a closer look at each of these components and see them in action. We start with the interactive guides. Welcome to Unreal Engine. In this interactive tutorial you will be guided step by step through the core features and workflows of the engine. Alongside the guided instructions, you will hear voice narration and have access to documentation panel that you can use as a reference at any time while learning. Feel free to pause, replay the narration, or review the written explanations as you explore. Your first task is simple. Take a moment to look around and become familiar with the viewport. Hold down the right mouse button and move your mouse to rotate the camera. Use this to freely look around the scene and get comfortable with navigating in the editor. Yes, just like that. Congratulations. You are now officially piloting the viewport camera. Move using WASD while holding the right mouse button. If you bump into a wall, that's fine. Every great developer has done that at least once. Great! Now head toward the glowing marker. Very good. Now doing a look and move around was easy, right? But our goal in the editor isn't just to observe. We want to build stuff. So let's first select an object. Simply click on an object with the left mouse button. Okay. With the selected object you can move it with W, rotate it with E and scale it with R. This you should know by now if you come from other game engines or a 3D modeling tool. If you're completely new to 3D, you learn now something quite industry standard. It is really among the first things to know, like how to walk before rushing anywhere. So let's practice that a bit. Select an object and move it, at least a few meters away by dragging one of the axes from the object towards your desired target location. If you do not see the move axis, press W. This will switch to the correct transform mode. Good. Now let's rotate an object. Pick an object and press E to enter the rotation mode. The axis should look different now. The motion you do here is just like in real life. Drag along 1/4 circle and see what happens. Got it? It's marked in such a way that you actually rotate around the desired axis intuitively. The red quarter circle handles marks the rotation around the x-axis. The green quarter circle handle marks y. The blue one is the handle for a z rotation. Now press R and scale the object. Make it bigger or smaller. Very good. With these very few things you learned today, you can actually help me to find my 6 boxes and place them on the teleporter platform. If you don't find them, make use of the Outliner tab. They should be named My Box. Double click them to move instantly to it. And if the Outliner tab is missing, go to Window in most top menu bar and select Outliner. First option. Remember, a total of 6 boxes need to be placed on the teleporter platform. Thank you, you have completed your first mission in the Unreal Engine editor. If you want to jump to the next map, pick one in the left navigation bar. To switch to another section, pick one in the right navigation bar. See you there. This map covers some useful tricks and techniques for using Blueprint in your levels. Included are some randomization examples, creation of object arrays, as well as gameplay behavior, such as tracking spotlights and working doors. What you're looking at here is not a traditional tutorial. There is no video on a second monitor, no alt-tabbing, no guessing whether what you did was correct. Everything happens right here inside the editor. When a student starts a guide, they are placed into a structured sequence of steps. Each step comes with audio instructions along with visual content written in Markdown. That means text explanation, images, even embedded videos or links. So the student is not just told what to do, they are shown in multiple ways. The expectation is simple. The student listens to the current step, performs the action inside the editor, then receives feedback automatically. But that feedback is not static, it's continuous. As the student works, the actions are being evaluated in real time. When everything is correct, the system responds immediately. You get a positive confirmation, and the system automatically progresses to the next step. No second guessing, just flow. And sometimes before moving on, the system even gives a small moment of positive reinforcement. Not constantly, because too much feedback becomes noise, but the right amount can reinforce the learning. And all of this happens seamlessly in the background. So what you end up with this is a system that watches what you do depending on a set intent, gives you space to experiment, and moves forward when you are ready. That's the key idea behind interactive guides. You're not copying instructions anymore. You're being guided through a process where the raw outcome can differ. Now let's take a look at how this extends beyond guided steps into evaluating full result. Render versus reference comparison system. This is where PRISM evaluates a student's complete implementation, not step by step, but as a full result. At any point, the student can take the current setup and compare it directly against the reference scene. The diff is able to highlight even the smallest deviations. The system compares the renders and outputs the difference per pixel. And based on a defined threshold, meaning a maximum number of allowed incorrect pixels, the result can either pass or fail. So it's not just visual feedback, it's measurable validation, but it doesn't stop at static scenes. The system also works with dynamic content. For animations, the system freezes the evaluation at a specific timestamp, so both reference and student outputs are compared at the exact same moment. And for procedural or random generation, I enforce determinism using a fixed seed, so both sides produce results which can be meaningfully compared. That means this component can handle static environments, animated sequences, and procedural worlds. Here's an important design decision. The student is not forced into a single solution, because in many cases, there are multiple valid ways to achieve the same visual result. So the component of this framework is designed to evaluate outcome, not the internal steps. On the instructor side, the setup is also very flexible. The reference assets actually exist inside the same map as the student setup. So the entire environment is shared. No duplication, no separate scenes. But in a real deployment scenario, the student would never see those reference assets directly. Instead, they only receive a reference render or texture. The instructor, on the other hand, can generate those references using the full asset setup. And because both systems live in the same map, everything stays consistent. No duplicated levels, no parallel environments, no extra maintenance. Just a single scene that can act as both student workspace and reference generator, controlled by a simple flag. And that's what makes this part of the system powerful. It doesn't just compare results. It unifies the entire workflow into a single reusable environment. Here we spot the differences between the just-made reference render and the actual implementation done by the student. The M_comparison shader helps to check upon those visible deviations directly, unlike the full pixel by pixel difference value output. This helps the instructor to ensure that their reference render is actually achievable and to fix the issues such as non-determinism, lighting, or other artifacts which could hinder the comparison system later when judging the student submission. Now, while render comparison is powerful, it's not sufficient on its own. There are cases where node level validation is necessary. For example, when teaching something like timeline node, it's not enough to evaluate only the final output. The actual configuration matters. So I explored node validation more closely, not to replace render comparison but to complement it. Initially, this was implemented in C++, which provides precise control but introduces complexity. And more importantly, not every instructor is comfortable writing code to define validation rules. So I introduce asset-based diffing. Instead of writing rules, instructors create reference assets for each step. And the system compares the student's asset against the reference asset, checking properties, node connections, and differences. This does increase the number of files, but improves visibility and iteration, which became more important than minimalism. At the same time, rule-based validation in C++ remains available, particularly for flexible scenarios where multiple valid solutions exist. So in practice, both approaches complement each other. And also, learning becomes gamified. In this play mode, instead of guiding you step by step, you are dropped into a system that needs to be fixed. In this case, a lab filled with glitches, unstable setups, and faulty implementations. And you take control of a robot with a clear objective: restore the system so it works again, either visually or functionally or both as intended. But here is the twist: you don't solve everything in one mode. Part of the challenge happens outside of play mode. That's where you fix blueprint logic, correct implementation issues, and prepare the system so it can actually run correctly. Then you switch into play mode. Now you are inside the system. You control the robot, and this is where you tune and validate the result in real time. You adjust parameters, test the outcomes, iterate until the system matches the intended reference state. I added also an additional challenge here: energy management. Every action costs energy. Moving the robot drains energy, adjusting parameters drains energy. So experimenting comes at a cost. You can't just try endlessly. You have to understand what you're doing. That's the shift from following instructions to solving a broken system under constraints. You're not told exactly what's wrong. You have to figure that out by yourself. Identify the issue, fix the implementation, tune the system, and match the reference. And if you succeed, you receive coins, which is needed to unlock other sections. If you run out of energy before reaching the solution, you simply replay. If you just want to explore though, you can of course disable the energy cost and you are free to play with parameters as much as you like. That's the core idea of the sandbox. Learning becomes a play. In this example, you notice a broken switch. The student checks the blueprint, applies the fix, then tests again. You tweak parameters, adjust logic, experiment, and in that process, your skills are challenged within a game environment. Now, got the gears in motion. This is one very effective, if not the most effective way of learning in my opinion. Before looking at the results, I want to briefly touch on how PRISM is built. First of all, the entire project is standalone. That means both students and instructors simply open the project and everything is already there. The framework, its content, the logic, all integrated in one environment ready to use. From there, everything is accessible. All code, all assets, the entire system is fully exposed. The documentation clearly highlights which parts are intended to be extended or changed. So if you want to go deep, implementing another custom validation step, you can. Every layer is accessible. PRISM is built to scale. New content and validation logic can be added across the entire stack, from data-driven tables and interactive maps to blueprint scripting, all the way down to C++ for even the most fine-grained and custom validation. And even at its current stage, PRISM already demonstrates what this project can become. A scalable framework that goes far beyond a fixed set of tutorials, potentially extending into entirely different domains of interactive learning. My goal with this project is to make users more productive and more immersed by turning learning into an experience that guides you, observes what you do, and helps you move forward step by step. And according to my research in EdTech, that's exactly what defines a good mentor. A key design decision was to make the system as data-driven as possible. That means instead of hard-coding the behavior, most of the learning content, progression and validation logic can be defined through structured data. This makes the system easier to extend, easier to scale, and easier to maintain. For the tutorial system, I used a web-based approach for content rendering. The tutorial widget includes an embedded browser that parses Markdown. This gives a lot of flexibility. It allows rich formatted text, embedded images, videos, links, and even efficient formats like compressed web images. So content is not limited by engine UI, it behaves more like a modern documentation system. At the same time, not everything is web-based. The navigation, the sidebar, the controls are built using Unreal's native UI system. That was intentional. Because while the web layer is great for displaying the content, it wasn't ideal for responsive interaction and smooth navigation. So the system combines both, web for flexible content, native UI for responsive interaction. For the comparison system, one of the main challenges was precision. When comparing two scenes, you don't want noise. Things like fog, post-processing, or unrelated visual effects. So the system selectively filters what actually matters, ensuring that only relevant differences are evaluated. And finally, for the sandbox experience, a lot of focus went into the interaction design. Adjusting parameters needed to feel smooth and intuitive. So instead of discrete inputs, the system uses analog controls, allowing values to be changed continuously in real time. The goal here was simple: make interaction feel natural. Now, what does this actually do for the learner? When I tested these components, the reaction was immediate. It felt different. There is a certain relief in knowing that something is watching what you do. Not in a controlling way, but in a supportive one. You stop second guessing. You stop asking yourself, did I do this right? Should I check again? Because the system answered that for you. It reminded me of a very familiar feeling when a compiler tells you build succeeded. That moment of certainty. But here it's even stronger. Because it doesn't just confirm at the end, it presents throughout the entire process. And that changes how you work. You become more focused, more relaxed, because if something is wrong, you will know. And if it's right, you can move on. And most importantly, you are actually doing the work. You're not copying steps from a video. You're not comparing your screen to someone else. Your workspace becomes the source of truth. Your action creates the result. And because of that, it starts to feel like you figured it out yourself. That's a very different kind of learning. Looking forward, this approach is not limited to Unreal Engine. While some validations are engine-specific like blueprint checks, others are not. You could validate interactions, behaviors, outcomes, which means this framework could extend into educational games, interactive simulations, or entirely different learning domains. At its core, this is about interactive learning. We already know the most effective way to learn is not by watching, but by doing. By trying, by failing, by adjusting, and eventually succeeding. What PRISM shows is that even in a complex tool like Unreal Engine, it's possible to guide that process in real time. That opens up a new format of teaching. The instructor is no longer just recording content. Instead, they design an environment, a system that ensures the student actually progresses, not just follows along. And from an economic perspective, this is also powerful. Yes, the initial setup takes time, but once it's built and scaled, it becomes reusable, consistent, and essentially free to distribute. Most importantly, it does not go out of sync, because if the project runs, then everything inside it is still connected, still functional, still valid. That's something traditional learning formats struggle with. They age, they break, they become outdated. So to conclude, PRISM aims to rethink how we learn complex systems by turning traditional learning into something interactive, responsive, and guided in real time. Because in the end, the best way to learn is to actually do the work, while continuous feedback keeps you on track, focused, and moving forward. Thank you very much for your time, your interest, and your support.